If you carefully watch a pot of water boil, you'll notice that the bubbles of gas do not form at the surface. Rather, they form below the surface, often at the bottom of the pot. Evaporation occurs at all temperatures, but why does boiling only occur at the boiling point? The formal criterion for boiling is this. Boiling occurs when the vapor pressure of a liquid equals the external pressure. That statement is somewhat confusing, but consider what goes on inside a bubble that would form, or at least hypothetically form, at different temperatures. Here again is the surface of our flask of water, but now let's imagine a bubble that forms underneath the surface. Inside that bubble there are gas molecules. Being a gas, it would have a pressure, but what is the pressure inside that bubble? It should be the vapor pressure of that material at whatever temperature it is. For example, with water, if this bubble were to form at 25 degrees C, the pressure inside the bubble would be 24 millimeters of mercury. We're talking about boiling, and this definition that for boiling to occur, vapor pressure has to equal the external pressure. It suggests two ways that we can boil. One, we can increase the temperature of the liquid such that its vapor pressure comes up to the external pressure, like we're doing here on a hot plate. We've got a flask of water boiling. But it also suggests that maybe we can change the pressure, the external pressure, to come down to the vapor pressure at a given temperature. So I've got my vacuum pump in the jar again here that we've seen before. And I've got a flask with a little bit of water in it. Now it looks slightly blue because I put a little bit of blue food coloring, so perhaps we can see it a little better. There are some boiling chips in there. Rough surfaces help liquids boil a little bit better. And just to make sure everything is right here, we're going to check the temperature. And the temperature of this water right now is 18 degrees C. So what I'm going to do is take my flask and put it inside the jar, like that. And then we'll put the jar back on the plate. And again, when we turn on the vacuum pump, we're going to suck air out. And the pressure inside the jar is going to go down. Well, it's going to take a while to go down, so let's think about this definition of boiling one more time. Again, if you were at room temperature, and if a bubble were to form at the bottom of a flask at room temperature, we ask what is the vapor pressure inside that bubble? Well, it would be the vapor pressure of water at that temperature, which would be about 24 torr. But pressing down on the top, the air pressure is 760. So that bubble at 24 would collapse. Go up to 50 degrees C. Vapor pressure is going to be higher. So you form a bubble at 50 degrees C, vapor pressure is higher, but not 760. 760 pressing down from the top, that bubble will collapse. Go up to 70 degrees. Form a bubble. Vapor pressure inside that bubble. Not 760, some number less. 760 pressing down, the bubble collapses. Go up to 90 degrees C. Vapor pressure inside that bubble at 90 degrees C is still 525 torr. 760 pressing down from the top, the bubble collapses. Not until you get up to the temperature of 100 degrees C where a bubble forms, the pressure inside that bubble is now 760. 760 pressing down from the top, the bubble persists and can grow and come out of the liquid. Let's zoom in on our flask. Can you see the bubbling? Water is boiling inside that flask. What we've done is reduce the pressure inside the jar such that it has come down to the vapor pressure of water at that temperature. It started out at 18 degrees C. And it will continue to bubble away. So we get boiling at reduced pressure. So we can go ahead and turn off the pump. And if we open up the tap at the top, let air back in, the boiling should stop. Because now we're increasing the pressure, and the vapor pressure inside any bubbles that could form is no longer enough to persist. So students will often ask, did that water get hot when it was boiling? Let's see. We'll take the jar off, take the flask out. Ooh, actually, is it hot? Well, no, it's actually cooled down. And if we can put the thermometer in, it hasn't cooled down greatly. We'll just let it equilibrate for a minute here. Why would it cool down? Well, keep in mind that when water goes from liquid to vapor, that's an increase in its potential energy. You have to put energy into the molecules in order to get them to go from the liquid to the vapor state. On the hot plate, we do that because we're continually inputting heat, inputting energy from the hot plate. In the flask, when we boiled at reduced pressure, where did the heat come from? We weren't adding any heat to the jar. It could only come from itself. Water had to convert some of its own kinetic energy into potential energy in order to get the boiling to accomplish. And in fact, the temperature here is down to about 14 degrees C, so it actually has cooled down.